This is Inspired in Higher Ed, My Favorite Paper, the podcast exploring inspirations driving research from faculty and professors.
From groundbreaking discoveries to curious passions, our guests reveal the journey that led them to their academic interests.
So join us, Dr. Blackburn,
and Dr. Grant Clayton,
to get inspired in higher ed with My Favorite Paper.
So my full name is Terrence E. Boult, but I go by Terry, so that's the way everyone calls me. If they call me Terrence, I know it's spam.
The guest on this episode, Dr. Terry Boult, is an Pomar Endowed Professor of Innovation and Security. He has a unique position on campus as the co-director of the Bachelor of Innovation degrees and the chair of the Pomar Institute for Innovation and Commercialization, which means he gets to work with companies, commercial projects, and defense contracts to improve surveillance systems, think video biometrics and such. He has won numerous awards, tons of grants with over 150 publications and counting. Find out more about Terry in the show notes.
So I started as an undergrad at Columbia University in New York City. I was then a grad student there for 3 years when I got my master's and PhD. I stayed at the same university because I switched from math to computer science. And then I spent 8 years on the faculty there. There was still a lot more for me to learn. I got my PhD so quick. It's like, no, I want to learn more. People think I must have loved New York City. I grew up on a farm in Pennsylvania. I thought I was going to love the big city. My love affair lasted about 2 weeks. I wasn't really a city guy. So I spent 7 years of my 8 years on the faculty commuting from Princeton Junction to Manhattan, a little over 2.5 hours each way. I got a lot of reading done on the train, but I spent 8 years there. Then I moved to Lehigh University, where eventually I helped found their computer science department, splitting it out of electrical engineering. So I spent 9 years there. And then I had some very odd educational objectives. In my second company, I became very aware of how badly we were preparing students for the workforce. I could not hire people with the skills I wanted, and I realized I was part of the problem. I was training computer scientists, but I was expecting someone else to provide all the other stuff that I needed, but no one was. Everyone was teaching their silo, and the silos together did not connect, and so it wasn't working. My real goal is the average student has a lot of potential, but only if we get them to learn to work together and across fields. And I chose UCCS as a place where I thought I could reach my educational mission, despite the fact that it was going to be a lot harder for my research mission. My friends all thought I was a lunatic. Many of them still do, but I'm doing it because I have a passion on the education side. I can do my research, my view, I can do my research anywhere. There's no one here that does what I do. There's no one here for me to collaborate on that, but I can collaborate on other stuff. So I've done grants with education and business and psychology, right? I can apply my skills in lots of domains. And that's what I really like doing, solving real problems.
Do you want to spend a minute or two describing what your educational mission was, how it's going?
Okay. It's all about two things. You have to be good in your field, but you have to actually learn how to work with people in other fields. Being well-rounded does not mean that I can quote Cicero. Being well-rounded means I can work with people who appreciate Cicero, even if I can't quote him. Right? I have to appreciate them and learn to work with them. And I designed a curriculum that is focused on actual interdisciplinary work, not go take this random class and that random class and put things together. And so that mission is, now we have 600 students across 22 different majors. It is about transforming the way people look at how to work on real problems in the real world.
The Bachelor of Innovation brings together emphasis areas in major courses, the Innovation Core, Cross-Disciplinary Core, and the General Education Core to train students in creative problem solving, entrepreneurship, and strategic thinking. Students can choose their major emphasis from 20 plus options and growing across business, engineering, education, science, and the arts. Learn more about the innovative approach in the show notes.
My family comes from a bunch of educators. Right? I really appreciate that being a teacher is not about just how do I teach. I have to work with the tech people in the school. If I want to make a difference in education, I have to be able to argue budget and where are they learning it. So the same is true if on cybersecurity. I can't be a cybersecurity major and not know how to talk to non-cybersecurity majors, because most of the security risks come from non-security majors. You've got to be able to cross those boundaries. And a curriculum that has almost all the classes are team oriented. We actually do team teaching because team teaching brings two different perspectives into the classroom, and we want students to see and model that, even to the point where we want to disagree. The two instructors are not supposed to agree all the time because that's not modeling most business worlds, where there's often disagreements and you have to use logic and rhetoric and whatever tools you have to convince one side or the other, right, to see where it goes. We want students to see all of that. So the education mission is about this multidisciplinary as opposed to interdisciplinary. Multidisciplinary is multiple disciplines working together, not I can do cybersecurity and psychology, right? That's interdisciplinary. I have two skills, right? Business and computer science is two skills. I wanted it broader than that. And so that was my educational mission.
I always liked that you colored somewhat outside the lines, and I said, this was originally inspired by papers that helped get people going, and you said, well, I really work on these interesting problems, and actually forwarded back some papers that you did. And so talk to us about the paper and what was going on and how this fits into your work, and as you said, major ideas that you're trying to go, big major problems you're trying to go solve.
I am going to roll back a little bit earlier and answer the question why my approach to research is I get excited by solving real problems. Early in my career, I decided I wanted to make an impact, so I want my work to have real meaning, which in my view means I have to solve real problems. I want to do what I consider fundamental research, and many people consider it fundamental because it doesn't have an application. In my view, it's only fundamental when it solves at least two different problems. Otherwise, it's a hack for one problem, but as soon as you can use it in two or three different problems, now you're talking about fundamental stuff. So I keep looking for problems that need to be solved. This particular problem of open set, which is, in my view, an important problem in growing of interest in machine learning, occurs because most machine learning things have a finite set of choices they're going to make. And if the answer is none of the above, right, I've never seen this in training, I should be able to say, I know, I don't know what that is. And that's not what machines have been able to do for a long time.
The paper topic that Terry shared with us is Towards Open Set Deep Networks from 2016 with Abhishek Bendale at the Samsung Research America. They proposed and tested an open set recognition model that is more accurate at identifying unknown concepts, in this case image classifications, than the basic deep networks. This conversation is going to get a little technical as Terry explains the deep network errors, and he does a great job at bringing it into a very applied logic space. You may want to grab the open access version of the paper linked in the show notes because the examples in that writing help it make a lot of sense.
In my second company, I was deploying systems and we were continuing having problems with our statistically based machine learning based systems because if they saw something they had never seen before, they would often get confused. So there would be a trash can blowing across a parking lot. It doesn't move like a car, so it assumes it's an intruder because it has cars, intruders, trucks, must be an intruder. And then the security guards get ramped up and it's like, oh, it's a trash bag again. You only have to go through 2 or 3 of those incidents and the security guards lose all confidence in your system. And so this is literally commercially a problem for us. We just couldn't get enough training data to get it to work. And around that time, I'd actually moved to UCCS. And so I ended up leaving that company. And 2 years later, started another one, and we ran into pretty much the same problem again. And it's like, okay, now we're classifying animals for a problem, and doing face recognition, both of which have to. You can't just recognize the terrorist watch list at the airport. You have to keep saying no, they're not on the list. No, they're not. So these class of problems were very broad. So it's like, okay, I'm going to look for a more fundamental solution. So I started in 2008. It took until 2010 that we got our first paper on it. In 2016, the world changed from support vector machines and earlier machine learning techniques to deep networks. So this particular paper came out of, okay, the world has advanced. How do we now apply some of our earlier ideas in the space of deep networks? And how do we make these networks learn? And since then, so I'm going to jump even to my current work, we're still looking at these problems. They've not gone away. We have not solved them. We made progress. We have things that are much better than they used to be, but they still get stuff wrong. Deep networks have some fundamental problems. I personally believe we really don't have a good handle on how they work. And since we don't know how they work, it's really hard to figure out when they do things wrong. So I've also done work in adversarial images where I can show it what looks to you and me like anything. I can take any image you want and make it the classifier think it's any other class I want. You can't see the difference, right? I have images. In fact, there's an image of me on my website that at the time I put it up, Amazon and 2 other commercial face recognition systems would say with high confidence it was Barack Obama. Because I can, so getting these networks to say, I don't know, and getting them to not be wrong is a very difficult problem. And so the underlying approaches we've been using come to a part of statistics called extreme value theory. So I dug into why things weren't working. And when they're failing, it's of course, it's the most extreme values in general. A classifier has, if you think about it, a boundary between class 1 and class 2. What we really want is a gap between class 1 and class 2 where you can say, I don't know, which means I got to figure out where's the real edge. Most systems don't find that edge. They choose the midpoint between the 2 classes to maximize their accuracy. It's like, it's closer to this class. Well, that's not saying it's in this class. It's closer is not the same question. So we developed a bunch of techniques using some advanced mathematical techniques using extreme value theory and some functional fitting. That is what the paper talks about on the known classes, is to say this is the limit of what's actually in this class. And after that, it's not in this class.
So we definitely want to, dig into some of those things and just let me know if this example is on the right track. So my spouse is an ML kind of guy, and when he was first kind of wanting to make this career move, he built this little like model to classify our dog, Gatsby. So he trained it on all sorts of photos of our little dog. This is Gatsby, this is a Gatsby, this is a Gatsby, and then introduced other types of dogs, and it did very well. Like, this is a Gatsby, this is dog. This is a Gatsby, dog. And then when we started introducing photos of a cat, which our dog is a Chihuahua mix, very small. He has cat-like essence. That's where really it got confused. And it was doing that instead of saying, I don't know what this is, it said, it's a Gatsby-ish. It's close enough to a Gatsby. We know it's not a dog. I think it's a Gatsby. And is that kind of what we're talking about? Like, it knows, but it doesn't know.
So those are good. Those are actually some of the harder examples. Right? Imagine that you showed it the couch or a cow.
Oh, very
right.
different.
It's even very different, right? It's still going to be, if the choice is dog or Gatsby, a cow will be one of the 2. Right? None of the above is like, so the subtle things of like subspecies of dogs or dog versus cat, those are good. And there's actually lots of practical things. But from a trash bag is not either a car, it's not even close, right? We were dealing with things that are so far from what I'm looking for. But if I only have 2 choices, it's got to be closer to one or the other. But there's a deeper thing that happens, which is not only would it say your cat was Gatsby, at times if you ask it, it's confidence. So the networks have ways of measuring their confidence. It would be super confident that it was Gatsby, not like it's Gatsby, but I'm not sure in terms of its confidence level. It's wrong and very, very sure about it being wrong.
Okay. So kind of adding that extra layer of both, let's be more comfortable outside the binary. Like, doesn't have to be just this or that. So
Right.
trying to introduce more options,
Right.
which machines are not built on, right?
Well, they can be. They
Okay.
were not being built. Lots of systems today have this as an ability.
Cool. And then also starting to assess its confidence.
Well, that's part of how you do it. So you could always take a system that has a confidence measure and say, I'm going to threshold the confidence. It's not confident, so I'm going to say, I don't know. Then the next question is, how do I build better confidence measures? Because if I get the wrong confidence measure, then I'm still going to get it wrong.
Think about classifications. You've got class A or class B. You were talking about obviously distances between classes and trying to build those distances. Most of my applied statistical work is actually on continuous values.
Mm-hmm.
So then how does it start to does a system like that deal with trying to create space when there really isn't? I mean, obviously there's an infinite number of numbers between 0 and 1, but trying to create space between classes on a continuous scale.
So actually all the work I do is in continuous space. Right? It's more complicated in discrete space, and almost no machine doing machine learning works in discrete space. The classes themselves might be discrete set, but by the time I take the input image input images are actually all discrete. They're 0 to 255 in 3 channels, but they quickly get converted by multiplications and stuff into floating point numbers. Not quite continuous, but pretty dense. But the way you find the boundaries in this space, right? If you think of a circle, right? I can put things on a two-dimensional plot. I can still find the line that separates the X's and the O's that I put in this plot. And so the question is, what's the best statistical position to put that thing? Now, deep networks are actually more complicated because our early work, we use these regular networks, regular classifiers where the features were given to us and we just try and separate them. Deep networks are trying to simultaneously learn what are the representations, what are the features, and how to separate them. So they become a more complicated problem. But the statistics is actually pretty straightforward. I find the most extreme example of this class, and I can fit a distribution. Extreme value theory says, if I look at the maximum of a maximum, depending on the rules of the distribution, that is going to come from one of three different distributions: Grumble, Frichet, or Weibull. If it's a distance, then it's bounded from below by 0. And there's only one choice, which is Weibull's, because they're the only one that's bounded. Frichet and Grumble are infinite in both directions. So we know what the distribution has to be. That's part of what our paper proves and gets into. And then we get to say, okay, now I'm going to fit on the data and say, okay, it must be this kind of distribution. So we take each class, sort of looks at its data and says, what are the most extreme distances in my current feature space? According to these Weibull distributions, we fit a Weibull on the tail. We don't care about what's going on in the middle of class. We only care about the extreme examples because that's what drives the final decision boundary. So we fit on those. And that's so in the continuous space, we're fitting a continuous distribution to a number of the extreme samples. And that's what we use to decide our confidence.
And for helping readers follow along, you said generally you like to do things that are solving at least two problems. Then make sure that, can you help us walk through, here are the two problems at minimum that you're helping to address?
So this particular paper, deep networks get used in hundreds of problems, right? At the time, maybe only 30 or 40, but they're used for image recognition, anything using an image recognition. But that includes like radiology, where we're making hard decisions about cancer or not cancer. They get used in drone images, DoD applications that I work in, where we're trying to answer questions about particular targets. They get used in biometrics, which is part of where I started, face recognition and things like that. So there's a whole range of problems that use images to make decisions. But it also gets used in text analysis. It gets used in audio analysis. And it even gets used now, it wasn't at the time, but now deep networks are being used on any large scale data problems within industry, where it's like, I'm looking for this. The problem is sometimes analogous to what's called anomaly detection or outlier detection. But OpenSet draws a slightly distinct difference from those, because I don't view the world as a binary problem. I view it as a multi-class problem and plus an outlier. So in a traditional anomaly detection, I'm saying it's normal or anomalous. Well, the difficulty of answering that question is actually very different than answering, I want to be able to correctly classify, say, 1,000 classes, 1,000 different things I can label. I'm a business. I want to label all these products that come down the line. I also want to say, I don't know what that is. Maybe it's a lunch bag, but I didn't learn on lunch bags. That problem is different because I have to make sure as I solve the it's unknown problem, I don't take some of the known classes and destroy their performance, right? So if I go back to your dog example, if there are just Gatsby and not Gatsby, that's a binary problem. And it's really, is it Gatsby or not? Outliers, Gatsby or not, maybe if all cows are not Gatsby, then maybe you're still okay, right? It's not Gatsby. If you called it the dog class, but maybe it's Gatsby, not Gatsby, that's a pure anomaly problem or outlier detection problem. If I care about getting all the average accuracy of each dog class correct, then it becomes an open set problem, because I have to keep each item on my set correct, but it's open because the answer is the set of known things is not closed. And the outlier class, in the most advanced form of this problem, which we call open world learning, not only do I have to detect these unknown things, I then have to learn them, because that's the real problem we as humans face, which is, I don't know what it is, and now I'm going to learn what it is. I'm going to get a label for it, gather some examples, and now add it to my set of things I know. And then I'm looking at the same algorithms are being now applied in a overhead surveillance. So you're looking at like Google map or Earth photos, right? And you're trying to answer questions. What's new? That's actually an inherent question in OpenSet, right? What has changed? And there are various agencies that want to know when there's random construction going on someplace in North Korea? Why are they taking apart that mountain, right? You want to know when things are happening, and there's just way too much of the earth for any human to ever look at, so you need automated algorithms. But if the error of detection of random new things, and the snow is landing on the ground in a different way, you've never seen that before. You have to be able to answer, that's a normal abnormality. It's in the set of things I'm supposed to put over here, but it's not, versus there's a crane in the woods. Those things have a lot of importance, and very few people are looking at them. So that's what the government pays me to look at. So.
And so that pivots amazingly well to the question about what advice would you give for aspiring researchers and aspiring research students on campus?
So in my research methods class, I actually talk about this, and this is I actually highly recommend you follow a sort of a two hunting approach. Okay, you want to be hunting big game, okay? But big game is hard to get, but when you get it, it's huge. On the other hand, you still have to eat. So you also hunt rabbits, right? So taking other people's stuff and doing some incremental work is great ways for, especially when you're training PhD students, right? For them to get their feet wet, to get some skills and build stuff up. When you go after big game, you might try very hard. So our first papers on OpenSet took us 4 times to get published in a good venue. It just kept getting rejected because it was so different from what everyone was doing. They kept saying, well, that's not how you, they just didn't get it. And we have to learn how to tell the story of our science in a way that they get. And I look at the world, I'm broken, right? I'm dyslexic. I don't see the world like most people do. So I've always had the advantage of, I don't see it the same, but it's also disadvantage because I have to then figure out how to put it in the right terms. Teaching my students how to do that, you want to have a balance of small incremental gains where they can, one, build their confidence and build their skills because stuff takes a while. And then one thing that you keep in the background that is, let's go hunting this big game. So the analogy from a hunting point of view is like 6 days a week, you hunt rabbits. 1 day a week, you go out on a big hunting party for big game and keep that as the open set problem I worked on. Actually, I have a different problem that I worked on for 9 years before I came up with a solution. It was an important problem. It wasn't being solved. I would try things and it didn't really advance the state of the art. Didn't solve the problem. No, every now and then I just come back to it. Right. I've got 3 patents. My second company had it as a product. Right. Third company. I go through this process, but you just keep coming back to it. And so every now and then you want to come back to, this is a hard problem, but it's worth solving. I'm not good enough in my view. Maybe I am, but I just don't feel that way to solve the wicked problems of the world. But that doesn't mean I can't choose something big and something small and alternate back and forth between them. Another thing people ask me, like, how have I been so successful with grants? And so I do have a process for grant writing and stuff that is maybe not what everyone else does. But the number one thing is submit lots of grants. In my biggest year, I submitted 42 grants in 1 year. And coming back to the collaboration way, there's no way to do 42 grants by yourself. You only do 42 grants because you collaborated with a bunch of people and you reuse some from last year that didn't get funded, and you go through the process. Right? Our town has lots of companies that people can work with, and that's another way. I've done lots of grants that are small business innovative research, SCTR grants. So if faculty are interested in like connecting and going after some of those, just reach out to me, because part of my role as an EPIC professor is to help commercialization on campus. And so if you need to partner with a company, I may not know one, but I can probably find one. And that process of competing for SBIR funds, if there's a way to commercialize your research, that money is much easier to get than a Department of Education or NSF or an NIH, right? Because your research has to solve a real problem. So this is the sort of bringing it back, right? One of the reasons I've been so successful is because I work on real problems. I can partner with people that are solving real problems and going after not the same money where I'm arguing why my problem is more important, but it's like, we have a solution. We're going to help people, right? That transforms how your grants get looked at.
You did talk about this a little bit already, but we always like to kind of start to wrap up with, your absolute maybe favorite place on campus. You've talked a lot about their favorite aspects, but yeah, what do you really love about UCCS?
The open space of campus is part of what, when I first moved here, right? I would go hiking on Austin Bluffs. I would take a lunch break, right? and I listen to papers. Right. So in fact, I very rarely read papers. I listen because of my dyslexia. So I have my app on my phone and I listen to things. So I'll go listen to a paper and hike up on the bluffs behind campus. Right. So things like that are you you can't do that at Columbia. I can walk in the streets of Manhattan, but it's just not the same. So the aesthetic beauty of campus is nice. But a lot of what attracted me here was the administration at the time, the openness about the ability to get things done. I've been frustrated at every school I've been at, so that's just normal as being a sort of entrepreneurial. Things move at an absolutely glacial pace, right? You can't do things. I frustrate them because I don't always follow all the rules properly, but so lots of good things on campus. So it's hard to pick out one that's my favorite place.
Thank you so much to Dr. Terry Boult for talking through problem-focused applications of machine learning and highlighting all the ways that multidisciplinary approaches help students. I definitely felt inspired listening back to these models and problem solving in higher ed. And thank you for listening to another episode with us. Please let us know your thoughts. You can comment directly from the YouTube app and Spotify, or send us a DM on Instagram. We are in_higher_ed with updates and day in the life content. The next episode will drop June 30th with a conversation about physics problems. Until then, stay inspired in higher ed. And mics are
And sound check.
You gonna sing for us?
Hmm?
I said, you gonna sing for us?
Singing is not one of my talents. I am tone challenged at best.
I can press play so we can start a support.
Okay.